So, hello everyone. In today's session of geometric dimensioning and tolerancing, we are going to understand about the topic which is about the angularity. Okay. So, we are going to learn about the angularity tolerance. Angularity tolerance is the first tolerance in the orientation control. Okay. So, this is the first orientation control tolerance, which is angularity. Okay, before getting into the angularity tolerance, please let us understand about the orientation control. Okay, so first of all we will understand the orientation control. So whenever we have a feature or a feature of size, okay, so whenever we have feature and feature of size is having angular relationship, okay, with the neighboring feature, so in that case, then we called it as a orientation control. Okay. So whenever feature and feature of size is having a relationship with the neighboring feature, angular relationship with the neighboring feature. Okay. So then we control it with the orientation control. If the angle is other than 0 degree, 30 degree, or 90 degree, 180 degree, and 270 degree, other than this uh, these angles, then that angle is called angularity. Okay, if these are angles are not there, so we can call it as a angularity tolerance. Okay, we can consider it into this. Okay, so in GD&T, the angularity is a three-dimensional GD&T callout that helps maintain a specified angle between a feature, line, or surface. Okay, between feature and feature of line or surface and a reference feature. Okay, so angularity is a control used to tolerance frame or feature control frame in the GD&T. It can be applied to a feature, surface, or to an axis. Okay, so angularity can be applied to a feature and feature of size for both. Okay, and it must be defined relative to a datum. A surface on its own cannot have an angularity with no other reference. Okay, so at least two features are required to provide the angularity tolerance. Angularity is the deviation from an ideal target angle, unlike perpendicularity and parallelism, which are specific cases of angularity. That angle can be any numerical value. Okay, so this is the GD&T symbol we use for the angularity, like this. A typical angularity callout is shown below the note that there must always be some reference in the third right box. Okay, so datums is the requirement. At least one datum is required to form to have a angularity tolerance callout. Okay, so here it is a datum A. This is the important for the practical application of GD&T. Okay, so datum is must required to apply the angularity or callout, because how you have to define and measure that datum could have a major impact on angularity control. Okay, so at least one datum is required for the angularity. From that, any angle can be measured. Okay, it can be 30 degree, 45 degree, whatever. So with the help of example, we will understand this. Okay, so an angularity callout can also be shown within the 3D model view. Okay, so in this is the example. This is the example we can discuss in very detailed manner. So let us take an example of angularity. Here is the planar surface. Okay, which is a feature is having a angle of 45 degree. Okay, so you can see this 45 degree angle between the this surface. Okay, so this is the surface we are having 45 degree angle. Okay, so for this, we give the angular tolerance. Okay, it is other than the 0 degree, 30 degree, 90 degree, 180 degree, and 270 degree. Okay, so it is having 45 degree, so we can consider it as a angular tolerance. Okay, so it is a related feature. So orientation is a having a related feature. Okay, so this surface is having relationship with the this surface. Okay, so these both the surfaces of the part, this surface of the part and the bottom surface of the part is having an inner relationship with each other. Okay, so this is a related feature. So we have to give the datum. Okay, so we have provided the bottom surface to the datum A. Okay, so we have given primary datum A. So this is considered to be the primary datum. because whenever we have to do a machining, whenever we have to inspect the part, we will take this datum into consideration. Okay, this is why into the orientation control we have to provide the datums. Okay, so in this case of Angularity, we have given the datum A as a primary datum. When we give like this interpretation, okay, is there are two parallel lines. So in this example, you can see over here, there are two parallel lines. Okay, this parallel line and this parallel line. There are two parallel surfaces which are 0.01 mm apart. Okay, so in this, there is a tolerance we have given 0.01 mm apart. Okay, so this is the distance between these two parallel surfaces apart at an angle of basic of 45 degree. Okay, so I've already told you this is the angle which is 45 degrees. Okay, the actual surface lies within these two parallel surfaces. Okay, so this is the tolerance, and within this tolerance, the actual surface is lying within this tolerance. Okay, so here can we have the surface like, so you can see it can have a surface like this in between this, but it should be within the tolerance zone. Okay, within these two parallel surfaces, which are apart 0.01 mm over here, any tapered surface can be considered to be right if it is within the tolerance zone. So you can see in the middle line is the actual surface of the part, which is not exactly at 30 degree, because if it is in any angle, it will be not in a at 45 degree. Okay, some angle will be different, but it is into a tolerance zone. Okay, so but the surface lies within the two parallel planes which are 0.01 mm apart. Then we consider that the surface is maintaining the angularity. Okay, so then we can consider that this this center surface is maintaining the angularity tolerance, also controls the form in this case. Okay, so this surface is also controls the form. Okay, why? This seems the surface is a planar surface. Okay, you can see this surface is a planar surface. It will control flatness of the part particular surface. So it will also control the flatness of the part. So here we can have an example where it is a plane surface with different angles. Okay, and one problem is also there, that the consideration is also there, that the surface can be like this. After manufacturing the part, in the two middle planes, we can have a we can have end up with the surface like this also. Okay, so here also again there are two parallel planes. So this parallel plane, which is 0.01 mm apart, the actual surface lies within this. Okay, the two surfaces. So the flatness maintaining between these two surfaces, and angle is also maintained at 45 degree. Okay, so this is about applying the angularity to a feature. So in this case, we have applied angularity to a feature. We have already learned that angularity can be applied to a feature, and angularity can also be applied to a feature of size. Okay, so now in this case, we have understood about the feature, that if the lie it within the tolerance zone, if the then the angle is considered to be in a right. Okay, so this is for the angularity to a feature. Now we will understand angularity applied to a axis. Okay, or to a feature of size. Whenever we are talking about the axis, so we are talking about the feature of size. So in this case of a circular feature of size, such as a cylindrical pin or a hole, the zone is expressed as a cylindrical zone. Okay, so in this example, you can see that this is a hole, and this hole is having an axis at the center. Okay, so this this axis is having a cylindrical zone. Okay, tolerance zone. So in this case, dia 0.01 mm is a cylindrical tolerance zone. Okay, around the axis of the solid feature. This zone is aligned to a basic angle with respect to the datum. So in this case also, the bottom surface we have given it as a datum surface. Okay, so in this case, you can see that this is the primary datum. We have given into the feature control frame also. So here in feature control frame, we have already given the datum. Okay. So in this case, what we have, there is a hole at an angle of 45 degree. So you can see this angle we have provided 45 degree. Okay, so this angle is at 45 degree. And so for that, we can apply the angularity tolerance, okay, which is 0.01 mm apart. So in this case, this tolerance zone, which is in pink color, so this is the tolerance zone, which is 0.01 mm apart, which is having a reference of datum A. Okay, so whenever we give like this, then we get a cylindrical tolerance zone of 0.01 mm in this drawing at the center. Okay, which I have represented over here. So the actual whole axis, lies within this cylindrical of 0.01 mm. Okay, so wherever the axis will lie, but it should be within the tolerance zone. Okay, it can be in a taper, but the axis should be in a tolerance zone. Okay, so here the actual axis of the hole is not exactly at 45 degree. So this axis will not be at 45 degree, but the axis is within the diameter cylinder of 0.01 mm, which is this. Okay, so this is how we get the angularity of a feature of size. Okay, so so you can see over here in the feature control frame, angularity which is maintaining at this. Okay, so whenever we apply the angularity to a feature of size, then we can apply then we can write it use the material condition modifiers. Okay, then we can use the material condition modifier. Okay, so in this case, if we are using plus minus dia 15 plus minus 0.01 mm. Okay, so in this case, you can see that at maximum material condition at 15.01, we have the tolerance zone of 0.01. At 15.02, we have the tolerance zone of 2. And at, when we move towards the tolerance zone, when at 15, we have the tolerance zone of 0.02, and at 14.99 we have the tolerance zone of 0.03. Okay, so as we move from maximum material condition towards least material condition, we get the more tolerance over here. Okay, because we have applied the maximum material condition modifier over here in the feature control frame. Okay, so this is how whenever we apply the angularity to a feature of size, we can apply the material condition modifier. Okay, so when the diameter is at mmc. Okay, so it will have 0.01 mm, and when it will move maximum material condition to the least material condition, the tolerance zone will increase. Okay, so this is all about the angularity tolerance when we apply angularity to a feature and when we apply to a feature of size. Okay, so this is all about the angularity tolerance. In the next discussion, we will learn about the second tolerance in the orientation control, which is about the perpendicularity, and next parallelism. Okay, so this is all about in today's session. Thank you. Thanks a lot.